The broadcast is now starting. All attendees are in listen-only mode.
Good morning and welcome to Pramet online training series. We're here in sunny Elgin near to Chicago. This is actually our fifth session focused on drill selection process today. So previous four sessions are located either at the dormerpramet.com, where you can find it in the Knowledge Base area, or you can go to our YouTube Dormer Pramet channel and find all those videos right there. If you have a question, as usually, please write those questions through webinar panel, and we will answer all your questions at the end of the session. And yeah, this training will be provided by a North American product manager, Gary Kirchhoff.
Thank you, Martin. This presentation will hopefully provide some helpful tips for selecting the right drills for your applications. When should you use a carbide, a cobalt, or a high-speed steel drill? Should you use a conventional or a split point drill? What point angle is best? What helix angle is best? How and why do certain materials change the drill you should select? Hopefully these questions and more will be answered today in our Knowledge Base External Webinar number 5 called Drill Selection Process. As you've heard before, if you've joined us before, safety is everyone's responsibility. Always maintain a safe work environment and be aware of exits and safe areas in case of an emergency. When on the shop floor, follow all safety requirements that are set forth by the manufacturer, as well as the personal standards you've established on your own. Always wear the proper eye protection as a minimum, as chips can fly out of the machine and tools can break or shatter. The very first step in the drill selection process is to determine the market area you are working with. This starts the process of narrowing down the types of drilling products we should be looking at. Our drills can be grouped to best address these three market areas. The top of the triangle depicts large-scale production and high productivity. This market area is usually best addressed with high-performance tools. Solid and coolant through coated carbide drills and Cobalt parabolic drills from our selection is typical. The middle of the triangle stands for mid-market or medium-sized job shop production. This market can be addressed using uncoated solid carbide, brazed carbide tipped, Cobalt, high-speed steel drills. This all depends on the material that's involved and the desired cost by the company. The bottom of the triangle shows the economy market, where price and perception is the driver. Normally addressed with MRO specific or general purpose drills. Hand drilling and drill presses are typical applications in this market. After deciding which market area we are working in and having a general idea of the tools we are most likely to use to best address that market area, we can look at a general production planning process as outlined here. The production planning process will include these 5 steps. Number 1, analyze the component you will be drilling. Number 2, choose the proper machine. Number 3, choose the right tool for the job. Number 4, apply the proper running parameters, establish cycle times, etc. And number 5, troubleshoot and analyze the tool failure mode in order to optimize the operation. Today we will focus on steps 1, 2, and 3, analyzing the component, the machine considerations, and tool selection. The first part of the process is to analyze the component or workpiece. This includes a good understanding of what you're working with and what requirements you need to achieve in order to produce a good hole. First, you look at the various aspects of the material you are drilling. We classify materials in 2 different ways. AMG, which is application material groups, mostly used for our round tool selection, or ISO material classifications, currently used mostly for our indexable tool selection. In analyzing the component, you must consider the machinability of the material, how the chips will form, and the hardness of the material. Our AMG material classification method and the ISO material classification can be covered in greater detail by contacting our territory managers application specialists, or product specialists. You also have to analyze the specifications of the holes you are drilling. This includes the hole diameter, the hole depth, and the hole quality. And you should analyze the many variables that will affect these specifications. These variables include the stability of the part in terms of thickness, or for a cylindrical part, the wall thickness if there is an ID and OD to the part. Secondly, the reach required. How far will the drill stick out of the tool holder? Third, rigid part fixturing. This is a must for successful carbide drilling. And fourth, is the drill rotating or is the part rotating? In analyzing the component, look at the blueprint of the finished part. Be sure to have a thorough understanding of the material and the optimal type of chip usually formed when properly machining this material. Be sure you are drilling through stable areas where the part will not move or flex as you apply force to that area. Consider the reach required from the tool holder to the part's surface to be sure your drill length isn't too long or too short. Remember, always use the shortest drill possible to maximize the drilling operation. Is the part stationary and the drill is rotating, or is the part rotating and the drill is in a fixed position? If the drill is fixed or non-rotating, can you use an indexable drill so you have the ability to come in and do secondary finishing operations with the same tool? In analyzing the component, start with the hole specifications, especially when you're drilling. The three most basic parameters are the diameter of the hole, what is the actual diameter, and the part print tolerance that's specified. The depth. The flute length must always be longer than the actual hole depth when drilling. Always be sure to leave at least 1.5 to 2.5 times D of flute length that is still above the part when the drill is at full depth. And quality, in terms of hole tolerance, surface finish, and straightness. The hole type and the required precision affects tool choice. The hole quality can be adversely affected by irregular or angled entry and exit surfaces and by drilling through cross holes, especially when the holes are not centered to each other. Make sure the workpiece doesn't flex or move when the force of the drill is applied. Moving or adding fixture supports closer to where the drilling force is greatest may be required so the part remains stable. Check the condition of the machine to clarify machine stability in general and especially the spindle stability. The spindle speed. Is the spindle speed or RPM enough for small diameters or for drilling non-ferrous materials? Coolant supply. Is the coolant volume enough for large diameter drills? Coolant pressure. Is coolant pressure enough for small diameter drills? Clamping of the workpiece. Again, check closely. Is the stability sufficient? Is the part fixtured properly? Horizontal or vertical spindle. A horizontal spindle enables better chip evacuation. Power and torque. Is the power enough for large diameters? If not, can a tree panning type drill be used, or can helical interpolation with a milling tool be used instead? Tool magazine. If there is limited space in a tool magazine, using a step drill or a chamfer drill can be a suitable solution to eliminate some tools by eliminating secondary operations. In rotating operations, the drill alignment is critical. If holes drilled are oversized or undersized, check first the drill if the drill is on center. If the center insert on an indexable drill or the chisel edge on a solid carbide drill chips, check again if the drill is on center. Turning the drill 180 degrees in the collet can sometimes solve these situations. Machine spindle and tool holder must be in good condition, and TIR, total indicator runout, must be kept to a minimum. In non-rotating drilling operations, the drill alignment is also critical. For indexable drilling, the total runout between the center line of the machine and the workpiece must not exceed 0.0012. For solid carbide drills, this TIR is much more critical. Anything over 0.0004 or 0.4 will drastically affect tool life and performance. Always remember, the less run out, the better. The indexable drill should be mounted so the top face of the peripheral insert is parallel to the machine's x-axis. Holding the drill properly is important to successful operations. Keyless chucks and drill chucks offer very limited gripping strength, which could allow the drill to spin or slip when cutting. Good collet holders such as ER type offer much better gripping strength. As with any type of tool holder, good maintenance is important. When chucking the drill, remember none of the flute should be inside of the chuck. If the operator is doing this due to length to workpiece restrictions, it is much better to recommend a shorter drill so the entire flute length can be outside the chuck and doing its job. Indicate the drill at the tip when the drill is in the holder and the holder is in the machine. Total run out should not exceed 0.8 on HSS and Cobalt and 0.4 on solid carbide drills. Tool holding is another machine consideration that is an important part of successful drilling. While Weldon holders and drill adapters may be an acceptable way to hold indexable drills, these types of holding methods are never a good idea when drilling with solid carbide drills. The tool illustrations on the bottom right of this slide illustrate how the tool is forced to be slightly off center because of the way the set screw locks it in place. This two-point contact does not maintain accurate centering like the other four methods shown. The other four methods provide multiple points of contact around the entire diameter of the tool's shank, which provides even pressure and accurate centering of the tool. Out of these holding methods, most accurate to least accurate is shown from left to right. The ER collet chuck tool holding method is still by far the most popular and economical way to hold most drills. Coolant supply is essential in drilling and influences chip evacuation, hole quality, and tool life. Use of internal coolant is almost always a plus when drilling. Always look for ways to optimize coolant delivery. Optimal coolant delivery will allow for better penetration, better chip flow, and enough coolant tends to keep the tool substrate from getting too hot, which causes premature failure as the cutting edges break down. Through the tool coolant or through spindle coolant is always your best choice when possible, especially when using solid carbide drills. Coolant through the tool is almost always best, except when drilling extremely hard materials. In these cases, sometimes a solid tool can be a better choice, as material removed from the tool for coolant holes can weaken the cross-section of the tool and cause breakage. Water-soluble coolant is most common and easiest to work with. These coolants work best at speeds above 100 SFM. Oil-based coolants will provide the best possible tool life, but these are best applied at speeds below 130 SFM. There are good and bad practices for applying external coolant to the drilling operation. This illustrates how the coolant must be aimed directly at the point where the drill meets the workpiece. This will allow for better penetration, as the coolant will tend to get pulled into the flute as the drill feeds forward. Always be sure the feed is correct so the chips produced are shaped like 6s and 9s. Long stringy chips can tend to block the coolant flow as they act almost like an umbrella, preventing the coolant from getting deep enough into the hole. More coolant is always better, so always use enough pressure and add extra nozzles to supply coolant from multiple directions if possible. For solid carbide, replaceable tip and indexable internal coolant is always the best. But external coolant can be used effectively on very shallow applications. External coolant should only be used when the length to diameter ratio is less than 1 times diameter and up to about 1.5 times diameter. Selecting the drill. Length to diameter ratios. Always use the shortest drill possible for the job. Even though there are many length options possible, the shortest length in combination with the hardest substrate will provide the best accuracy and rigidity for the application. This is especially true with high-speed steel, as longer high-speed steel drills will flex much more than the short high-speed steel drills due to the softer substrate. The basic industry standard drill lengths are called off here using industry terminology to specify drilling depths. Screw machine length or stub length drills are for drilling approximately 2.5 to 3 times diameter depths. Mechanics length drills are for drilling approximately 3.5 to 4.5 times diameter depths. These are available only in our Precision Light or MRO offering. Jobber length drills are for drilling approximately 5 to 6 times diameter depths. Taper length drills are for drilling approximately 6 to 7 times diameter depths. And extra length drills are for our R459 carbide drills are for drilling up to 8 times depths. And our high-speed steel extra length drills are for drilling up and beyond 20 times diameter depths. Common industry standard drill shank styles are categorized by these 3 popular types. Standard straight shanks. These are drill shanks, these drill shanks can also be called cylindrical shank drills, which means they do not have any flats or other modifications done to the diameter. Common shanks are also straight shank drills, but common shanks are used more on solid carbide drills and high performance drills, where the idea is to greatly reduce the number of collets an end user has to stock. Usually an entire range of drills from 3 millimeters up to 20 millimeters. Cutting diameters range can be up to 150 and over individual sizes. Those can all be held in only 8 collet sizes: 6 millimeter, 8 millimeter, 10 millimeter, 12, 14, 16, 18, and 20 millimeter collets. Straight shanks with tangs are for the purpose of driving drills, usually in handheld applications. Reduced shanks, available as standard in our offering, half-inch reduced with tri-flats, and 3/4 inch reduced shank sizes. And Morse taper shanks contain variations such as tapers larger than standard, tapers smaller than standard, coolant feeding with side or end entry type coolant holes. Morse taper drills are normally used in drill presses or mag drill applications. It has been noted by those engaged in production drilling of steels, especially deep holes and harder steels, that better results can be obtained by increasing the included point angle from the standard 118 degree to 130, 135, or 140 degrees. On the other hand, it has been found that cast irons and related softer materials can often be drilled to better advantage with smaller included point angles such as 90 or 100 degrees. Smaller included point angles, normally 118 degrees, used in mild steels and cast iron, distribute the cutting load over a longer length of the cutting lip, thus reducing the load. This reduced loading enables the cutting lips to better reduce wear. Plus, the smaller angle directs the flow of chips into the flute's gullet. Larger included point angles, anywhere from 130 to 140 degrees, are helpful with hard-to-drill materials because the chips produced are thicker. Most materials can be more effectively cut in the form of thick chips. The thicker chip also tends to reduce the amount of work hardening of most materials. Torque requirements are also reduced due to the shorter length of cutting lips. The conventional point is the most commonly used drill point. Properly produced, it will give satisfactory drilling results in a wide variety of materials. In use, this type of point may eventually require some form of web thinning when used on drills whose web thickness has increased because of repeated resharpenings, or on heavy-duty drills with heavier web constructions. The conventional drill point does not have the self-centering capabilities that a split point drill has. When spot drilling for better location, always remember the spot drill point angle should always be the same or slightly larger than the drill point angle. We offer solid carbide spotting drills at 90 degrees included, usually used for pre-chamfering the hole, 120 degrees included, usually used with 118 conventional drill points, and 142 degrees included, used for drill points that are anywhere from 130 to 140 degrees. However, if you're using a 130 to 140 degree split point drill, spotting for location is usually not necessary, as the drill will center itself in most cases. The split point was originally developed for use on drills designed for drilling deep oil holes in automotive crankshafts. Today, it is used on many designs of drills used in a wide variety of hard and soft materials. It can be applied to a variety of drill point angles, the most common being 135 degrees. The main advantage to this type of point is that the web thinning, which greatly reduces thrust and adds positive rake cutting edge that extends to the center of the drill. In many materials, this point will act as a chip breaker to produce small chips which can be ejected through the flutes. The split point minimizes skidding or walking of the drill point when starting a hole. This is a distinct advantage when portable drilling, hand drilling, or in a drill press where bushings cannot be used. The use of a split point drill can totally eliminate pre-drilling operations, saving cycle time and reducing cost for the manufacturer. Solid carbide drills versus HSS drills. Better machining tolerances. Solid carbide drills are stiffer and harder than HSS drills and will bend or flex much less. This enables them to machine to much closer tolerances. HSS drills will almost always drill slightly oversized and in many cases will require a secondary reaming operation in order to hold closer tolerances on the finished hole size. Better productivity. At similar feed, a cutting speed of about 300 to 400 SFM is possible with solid carbide drills, compared to an average of about 50 SFM with high-speed steel drills. The solid carbide drills will thus offer improved productivity over high-speed steel drills. The benefit with the solid carbide drills are high productivity, longer tool life, low cost of production, and the tool life with solid carbide drills is normally 20 times longer than with high-speed steel drills. The cost per hole and the total costs are in general 60 to 80% less as compared to high-speed steel drills. The figure is well worth considering, and these figures are something that a lot of purchasing people do not consider when they're looking at the cost of the tool. The actual production costs are what's more important. Straightness of the hole. Solid carbide drills are stiffer than HSS drills, and there's more precision symmetry in the manufacturing of these tools. This enables us to guarantee the straightness of the hole when drilling with solid carbide drills. However, there is a risk of drill breakage in the case of longer solid carbide drills because of the brittle nature of the carbide substrate. In typical operations, the reach should not exceed 12 times D. Hardened material. Solid carbide drills are hard and can thus be used for machining of hardened material up to about 60 Rockwell. Because most HSS drills are only marginally harder than that 60 Rockwell material we're machining, they are not really suited for these kind of applications. Easy to machine materials. Since solid carbide drills can also be used at low spindle speeds, both solid carbide drills and HSS drills can be used for easy to machine materials like copper, bronze, and aluminum. However, the solid carbide drills will always have the benefit of longer tool life and higher productivity. This is more than fully compensated by the better productivity of the solid carbide tools. Helix angles have evolved over the years to today's most common types being conventional, low helix, high helix, and parabolic. Slow spiral drills, approximately 12-degree helix, are designed to perform best drilling shallow holes in soft materials. Low spiral drills, very similar, approximately 22-degree helix, are also designed to perform best in softer materials. These helix angles are very similar in the way they evacuate the chips. A regular spiral or conventional drill, 28 to 30-degree helix, is most common and is designed to perform best when drilling shallow holes in steels and irons. The most widely used flute form in job shop drilling a wide variety of materials. You will find conventional jobber drills in almost every type of job shop you work with. A fast spiral drill, 38 to 40 degree helix, is designed to perform best in softer or gummy materials such as aluminum, magnesium, leaded seals, copper, wood, and plastic. The faster spiral is designed to carry more chips up and out past the entry surface of the part. Just like with slow spiral drills, this faster helix is designed to facilitate chip evacuation. The drill shown at the top of this page has a conventional flute form. You can clearly see the limited space for chips as compared to the two examples below that one. This limited space, along with a web increase, limit the most common use of this drill to standard drilling depths up to about 4 times diameter or less. You will notice the difference between the wide land or heavy duty parabolic and the narrow land or American style parabolic on the bottom. The narrow land parabolic has no land width but has a margin width that is about 30% wider than standard and a web thickness of about 38 to 40% of the diameter. The narrower land allows for greater chip volume, especially in softer materials such as aluminum and other free machining materials. Due to heavy webs, most parabolic drills will have 135 degree split points to direct the flow of chips straight up the flute and ease the thrust and the heat that would be generated by the wider web thickness. Another feature of parabolic drills, whether they be wide or narrow land, is they will have 38 to 40% helix angles for the purpose of escalating chips. Parabolic drills will be best applied where the feed rate can be controlled, so the drill doesn't pull itself into the workpiece too fast. Here you can see the difference between the parabolic profile and the conventional profile. The biggest differences noted are tool strength and the area for accommodating the chips. You will note that the conventional form is restricted, while the parabolic form is wide open and generous due to the rolled heel. This allows for greater chip evacuation when using the parabolic design. Again, these drills can be very aggressive, so applying the proper feed rate for the material is essential. This graph illustrates the tool materials and where they are positioned in terms of hardness and toughness. The harder the tool substrate, the more resistant the drill will be, resulting in longer tool life. The downside is the harder the tool substrate, the more brittle it is. The harder substrates are more likely to fracture or break when applied in adverse conditions. The softer tool substrate, the more tough the drill will be, which can allow successful drilling to take place even under adverse conditions, like poor fixturing, vibration, non-rigid setups, etc. The tougher substrates will offer less tool life, but are also less likely to fracture or break. Dormer Pramet offers drills made from most common substrates: high-speed steel or HSS, high-speed cobalt steel, which is HSSE or HSCO, solid carbide, usually depicted by HM, brazed carbide tipped, replaceable head or modular type, and indexable insert type from our Pramet offering. Based on the vast array of drills available to address everything from high performance to MRO applications, our very capable territory managers, application specialists, and product specialists can fine-tune the drill to the application aimed at providing the best possible product for the operation. There are several tool coatings in the market today. Tool coatings have all evolved from the original TIN coating, which was originally developed way back. Each of these coatings have been developed specifically for better performance or longer tool life in certain materials and certain conditions. This slide shows only some of these coatings that are in the market today. We offer drills standard that are coated with tin, TIALN, TIALN top, and ALCRN top. Anytime you see a coating offered as a dash top type coating, this only means that there is also a post-coating or smoothing process performed, which takes away any imperfections on the surface of the coating. This works almost like a polishing process, which can greatly improve the chip flow. Our surface treatments are steam oxide, bronze oxide, and purple bronze oxide. Although these surface treatments slightly increase the surface hardness, they are mostly applied to protect the drill from rust and corrosion. So now in review, these are just some of the more important things to address in drilling operations. The workpiece material and machining characteristics of that material, the condition of the entry and exit surfaces of the workpiece, the dimensional aspects and the quality of the hole. Are we drilling in a vertical or a horizontal direction? The tool material or substrate, the tool coating or surface treatment, the drill length required and reach needed. Do we need to reduce torque? And are there subsequent operations performed prior to or after drilling? So this concludes our 5th external webinar for 2018, the drill selection process. I could go on for probably 2 more hours about this, but obviously we have a time limit. So join us again next month for our continuing series of external training webinars. Thank you and have a great weekend.
So as of right now, we have no questions. So if you have any questions, you can send it back to us at cs@dormerpramet.com. We will be happy to answer that, or you just place your question through our YouTube channel under the video, and we will come back to you and answer the question. Thank you for your participation, and talk to you next time. Goodbye.